As we talk about data types in C, in addition to their values and operators, we'll also talk about their representations. But in order to understand that material, you'll need a good understanding of number systems. In previous semesters, many, but not all, students in this class have seen much of this before, whether in 126, perhaps in APCSA, perhaps in middle school or high school math classes even. But I want to make sure that everyone's refreshed on the topic and on an even footing for this class moving forward. I say without exaggeration that everyone here knows the decimal number system, and has since first grade if not before. The vast majority of human civilizations have used the decimal number system, presumably out of, without being ableist, biological convenience. Note, I have the word 10 an annoying number of times on this slide. Every single time I say 10, I mean the number 10 in decimal. As the comic on the slide observes, if we call 10 10 more generally, communication breaks down. So in the decimal number system, there is a set of 10 symbols. A number consists of the sum of the digits multiplied by their respective right to left starting at 0 powers of 10. Which is just a fancy way of saying that what you learned in elementary school about the ones place and the tens place and the hundreds place, that's what we're doing. So there are other bases besides decimal, and the good news is that everything you know about decimal works for them too. They have the same characteristics, except that they have a different number of symbols in their character set, and the powers that we're multiplying by are powers of their base, not 10. As an aside, I keep saying symbols instead of digits because the root of the word digit is that same biological counting convenience, just spoken in Latin. So let's talk about other bases. There is unary, coming from the Latin unus for one, and the ary suffix by analogy to binary, trinary, etc. In this system, there's one symbol, by convention 1, and the number is formed by just repeating that digit as many times as necessary to achieve the number. This sounds silly, but we actually use this with tally marks, so as long as we don't cross our fives, we've already used unary. But unary does break the idea of a sum of products of powers, so let's really begin with binary. The same rules we talked about with decimal apply to binary. Two symbols, 0 and 1, positional systems, so different permutations of the same symbols are not the same number, and the same sum of products of powers number formation. It's natural to use binary for computers because digital computers are built using digital circuits, each of which has only two states, on and off. If we think of 1 as on or hot or high voltage or connected circuit, and 0 is off or cold or low voltage or disconnected circuit, then in that sense, digital computers use the binary number system in their very essence. So a little bit of terminology here. A single symbol in binary is a bit. That's a compression of binary digit, which based on digits etymology is a misnomer. The byte, which is a term that dates to the mid-50s, is a coherent organization of some number of bits. In everything we're going to see, it's always 8 bits. Possibly my favorite vocabulary of the entire course, a nibble is just half a byte, so 4 bits. And to avoid the 10 issue from my previous slide, I'll pronounce these numbers as ones and zeros. So for example, 1000, not 1000, not 1000, or 1100, not 1100. Etymological aside, the numbers 11 and 12 are from 1 and 2 left over, meaning on top of 10. And 100 also, perhaps surprisingly, perhaps not, is from the Proto-Indo-European root for 10. So all of these would be bad numbers to use when counting in some base other than decimal. All right, that's probably enough linguistics for a COS lecture. Here's a table of binary values 0 through 31. I personally found it useful to memorize 0 through 15, but at least know these heuristics. 1 and then all zeros is a power of 2. It's namely 2 to the number of zeros. All ones is 1 less than the next power of 2. 10 is 1010. This mnemonic is worth being the only time I'll break my rule about bits don't say 10, 11, 100, etc. So 10 is 1010. So to convert from binary to decimal, you simply have to expand the positional notation and compute the sum of products of powers. Think of this as computing the polynomial. Note the notation. I'll use a subscript b after a binary number to indicate that it is indeed binary. Absence of a subscript indicates decimal. So to convert the other way from some integer, in this case represented in decimal for convenience, we have to find the appropriate positional notation. One way to do this is the subtraction method. Find the largest power of 2 that is less than the target number, subtract it off, put a 1 as the coefficient of that position in the polynomial. If the largest power of 2 is less than a subsequent power of 2, or the largest remaining power of 2 is less than a subsequent power of 2, put a 0 in the coefficient of the positional polynomial to skip that term. So for instance, here we have a 1 in the 32's place, but then what's left is 5, so we don't have a 16 and we don't have an 8. So we put zeros in those locations. Another way is to repeatedly divide and then read the remainders bottom to top. No surprise these are equivalent, as division is repeated subtraction, but keep this in mind because this applies a little bit nicer or easier for other bases. So more people seem to know about binary than hexadecimal. So when you first see hexadecimal or hex, it looks complicated, but all the same rules you know about counting from decimal apply. So hexadecimal is base 16. Unfortunately, being that we actually use a base 10 is base 10 for us, we run out of symbols. We have 0 through 9, and then what do? So by convention, it's A through F, can be either capital or lowercase. In C, we have a prefix for a number that's represented in hexadecimal, and that's the number 0x followed by the hex number. And so why is hex so common as a number system in computer programming? Well, it's a handy abbreviation for binary. Because 16 is 2 to the 4, each hexadecimal digit, is a nibble, is 4 bits. So again, you definitely should memorize A through F for 10 through 15. It's probably useful to memorize each nibble 4-bit string too, but maybe not absolutely critical. If you've done one memorization and you do the other memorization, it's just a lookup table. So hex to decimal integer, we're going to just expand the positional notation and add. So here we have 2, 5 hex is going to be 2 times 16 to the 1, 5 times 16 to the 0, 32 plus 5 is 37. For going the other way, decimal to hex, we can use the division mechanism that we showed in binary, but instead of dividing by 2, we're going to divide by 16. So 37 div 16 is 2, remainder 5. Then we've got 2 div 16 is 0, remainder 2. We read bottom to top, and we end up with 2, 5. Binary to hex conversions are even easier. Working off the observation that each hexad is a nibble, all we have to do is substitute in one direction or the other. So when we see 1010, we know that's an A. And when we see an A, we know that's 1010. If there aren't enough bits, we can add bits to the left side, because just like in decimal that we're used to, the number 000000217 is 217. All the leading zeros didn't matter. So we can freely add those extra zeros to the left side to get enough bits to form a full hexad. So here's a quick quiz. Go ahead and pause the video at this point and do the conversion. See what you come up with. So the correct answer here is that it's 42 in decimal. It's 2 plus 8 plus 32. We could also have done this, like the slide said, convert to hex first. When we convert to hex first, what we do is we split it up into hexads. So we have the right hexad is 10, the right 4 bits are 1010. That is the hexad A. And then on the left we have 10. We can pad with zeros. So that 0010 is a 2. Once we've done that, we have 2A in hex. We could just compute that as 2 times 16 plus 10. That's 42 also. So there's a number of different ways to do this conversion. So the octal number system is the last number system we're going to talk about. Again, it's the same. It's a different subset of symbols, but the same rules. Octal is another handy abbreviation for binary. Just like 16 was 2 to the 4, so every hexit was 4 bits, every digit in an octal number represents 3 bits, since 8 is 2 to the 3, 2 to the third. You'll actually see this in Linux, where file permissions are read, write, and execute for a file, and the chmod command that you saw just very briefly in the intro to Linux and Bash lecture takes octal numbers as a representation of that. So 6 is read and write but not execute because it's 110. 7 is read and write and execute because it's 111, etc. So next lecture we'll be jumping into part 2 of the crash course dealing with numeric data types. And then in part 3 we'll tackle arrays, strings, and where the rubber meets the road in C, pointers. Until then, work hard on assignment 1, which is due Thursday the 17th.